Has this ever happened to you? Oh no, my fishy died.
Have you tried checking your parameters?
My para what?
You know, the pH and hardness of your water?
I'm peeing in my what?
No.
Well, definitely a bit of an over-exaggeration. I definitely see this sort of thing in fish keeping forums all over the internet a lot. Someone uses their 7-in-1 test strip and has no idea what the readings mean or what they're even testing for. Think of it like this. At its most basic level, fish keeping involves two parts. That is, fish and water. Ammonia, nitrites, and nitrates are one of the first things beginning aquarists learn about. While these are important to measure in their own right, other parameters are just as vital to the health and well-being of your fish. Let's dive into it. To understand much of anything about water, we need to understand its molecular structure. Water is composed of 2 hydrogen atoms and 1 oxygen atom, which gives rise to its unique properties. Water is very stable and generally unreactive, but that's not to say that it doesn't do things. Without getting too technical, water is a polar molecule. This means that while it has an overall neutral charge, one side tends to be more positively charged and the other more negatively charged, like a magnet. Its magnetic forces keep water liquid at much higher temperatures, as most molecules as small as water are gaseous at room temperature. Not only do these magnetic forces affect water's state of matter, it also allows water to be what is known as the universal solvent. Simply, most molecules are comprised of dissimilar elements, meaning that they too have some magnetic forces. Well, due to different causes, both sugar and salt will readily dissolve in water. Because of the sheer amount of chemicals that dissolve in water, water is never just water. To demonstrate the universal solvents of water, we're going to evaporate some water to show what's in the water. Here we have a sample of tap water that I've gathered from earlier, and this is a sample of distilled water with a little bit of electrolytes added to it. Now we're going to leave it out in the sun for a couple hours and see what happens. All right, so it took a couple days, but it had finally evaporated. So here we have the smart water. You can see that there's not a whole lot of residue, but there is some residue. That one that's really fun is the tap water here, because there is a lot of residue, showing water isn't just water. Which brings us to our water parameters. These measurements allow us to identify and quantify what else is in our water. Water has such powerful magnetic forces that it can rip itself apart. It will strip a hydrogen ion off the main molecule to make an H+ and an OH- ion. pH is simply a measure of the concentration of hydrogen ions in a solution. In pure water, these ions will exist in a balanced state, but most water that we come across is not just water. Things that get dissolved in water will affect this balance between the ions. When the ions are balanced, the water rests at pH of 7, meaning that hydrogen and hydroxide ions are balanced. When balanced, the ions tend to stick together, only occasionally becoming ions. As pH moves lower, the concentration of hydrogen ions increases, making the solution more acidic. If it shifts higher, this makes the solution more basic. Why does this even matter? Because of their charges, ions can be quite reactive. If they don't have a good enough balance, the water solution starts to get to a point where the ions will react with just about anything, including very stable organic compounds that make up fish and other living things. The beneficial bacteria in an established aquarium will stop thriving at or below a pH of 6 and will not be able to convert ammonia to nitrate very well. Most aquatic organisms will die below 4.5 pH or above 9.5. Most aquarium fish will stop thriving outside of the normal range of 6.5 to 9 pH. Understanding what pH is essential to monitoring and adjusting it. Another one of the ways we quantify the other things dissolved in water is by the water hardness. There are 3 different measures of hardness: general hardness, carbonate hardness, and total dissolved solids. In nature, these parameters are connected, so in water with a low general hardness, you would expect a low carbonate hardness and total dissolved solids as well. In the home aquarium, these measures are manipulated independent of each other. For example, water softeners will only lower the general hardness but leave carbonate hardness alone. When talking about water hardness, people are usually referring to the general hardness. General hardness is simply a measure of calcium and magnesium in water. These are essential nutrients for aquatic life, which is why it's important to have some hardness in the water. Fish get a lot of their minerals from the water in addition to their food, but too much of a good thing can be bad. If the water has too many minerals, it can stunt the growth of fish and cause organ damage for some. Fish can adapt better to higher mineral content in water than low mineral content. Carbonate hardness measures the content of carbonate ions and bicarbonate ions in the water. The KH of water is an important element in maintaining the pH of water, as carbonates help to stabilize the pH. At a roughly neutral pH, bicarbonate will be the most common form of carbonate in the water. If something lowers the pH, the bicarbonate is able to take up another hydrogen ion due to its charge. If something raises the pH, the bicarbonate will donate a hydrogen ion to become a carbonate ion. If you have no carbonates in your water, the pH will fluctuate constantly due to other chemical reactions that sustain life in water. Alrighty, we have here an experiment for you. Now we have 2 test jars of water here. We have some tap water from my own garden hose, and we have some smart water here, which is in theory distilled water without any carbonate hardness. Now what we're going to do here is we're going to measure the pH swings when we blow bubbles into the water, which should in theory affect the pH. This is what happens in your aquarium when your fish are breathing. So with my handy dandy science straw, we're going to test the swing of the pH with carbonate hardness. Now we'll give it a second to adjust. Notice how the pH didn't change much. In fact, it stayed relatively stable. Now here's what happens when we blow bubbles into the non-stabilized water. Notice how the pH dropped a good 0.1 or 2. This means that the pH actually changed a lot with the bubbles. This happens in your aquarium without carbonate hardness, and that's why it's important. Going through the footage from earlier and realized we cut off the recording too early when we were measuring the pH swing of the non-stabilized water. Now, it took a minute to adjust, but it ended up down near 6.5, which means that it swung about half a degree of pH, and that was just a little bit of blowing bubbles. Now you can imagine what would happen over time with fish breathing in the water. Another metric that can be used to measure water hardness is total dissolved solids. This will measure everything in the water that isn't water. This includes things that are already measured by general hardness and carbonate hardness, but also sodium, heavy metals, and many others. Because of how indiscriminate a measurement TDS is, it's not typically used in the home aquarium. Well, that's all we have time for today. Join us next time for part 2, where we discover the more biological side of our water.